Hello, how's it going? Alright, let's make sure we're going. Yes, it's going good. So, let's start. I've got a lot of questions lined up today. Pretty much the deal here is that there's lots of different types of questions you can do with Newton's laws as we know them. And so this is a good opportunity to see a bunch of examples where we do it because they're fun. Fun. It's fun. Okay, so I've got a bunch of them. In each one, I'll try to stick to the notation and the procedure that we've been going through in class. The idea here, though, is that we're going to apply lots of things we've been talking about in class in different ways. So, first question, 25. If you have any questions, ask for them in the live chat. I will be here. Question 25 goes like this. All right, hold on. Let's make sure you do. Yes, okay, you can hear me. Good. Okay, so question 525 goes like this. Bonnie and Clyde are sliding a 500-kilogram bank safe across the floor to their getaway car. The safe slides with a constant speed if Clyde pushes from behind with 385 newtons of force, while Bonnie pushes forward on a rope with 350 newtons of force. What's the safe's coefficient of friction on the bank floor? So we'll start out by drawing. Here you go. There's someone, Clyde, pushing from the back, and then Bonnie pulling forward on this rope. Okay, so what's the mass? 300 kilograms. Okay, so the deal is we know how strong these forces are. We're given how strong the force pulling forward is, and we're given how strong this force pushing forward is. So we'll incorporate those in the free body diagram when we reach it. The first step to this analysis is you talk about the acceleration. What's the acceleration in the x direction? What's the acceleration in the y direction? This question specifies that they're moving with constant speed. Constant speed means no acceleration. Or rather, it's not going in a circle, so it's constant velocity. No acceleration. So once you know about the acceleration, you can talk about the net force in the x direction and the net force in the y direction. So each of these are 0. Now let's analyze the forces on them. There's going to be a force from gravity. What other forces are involved? To answer the other forces, we need to talk about what the object's touching. It's touching the floor. So that's the normal force. Oh wait, in this class we call gravity weight. So there's the weight, there's the normal force, there's the force from Bonnie, and there's the force from Clyde. And also, presumably, there is a friction force. How do we know there's a friction force? Well, for one thing, we can guess that there would be. But for another thing, we know that because there's no acceleration, all the forces have to cancel out. So there has to be a force pushing to the left. Let's analyze each of these forces. In the x direction, it's 0. In the y direction, I don't know how strong it is. I'll call it n, variable n. The weight in the x direction, I know that's 0. The weight in the y direction, that's going to be 9.81 times 300. Hold on, let me calculate this. So this is 2,943 newtons. All right, what other forces are there? There's no room there. I'll keep writing down here. There's the force from Bonnie. Y. Force from Clyde. And the force of friction. So what are each of these? I know based on the clues given that the y direction forces of each of these are 0. Force from Clyde, he's pushing from behind to the right. So it's 385 newtons to the right. Bonnie pulls 350 newtons to the right. And I don't know how strong the force is from friction, so I'll just leave it as an F. So the strategy at this point in time is to write down everything you know. And by that we mean not just provide variables for the things you don't know, but also you'll note here that even though I don't know how strong the normal force is, I do know what direction it is. And so that's a piece of information that gets jotted down as I make these notes. Okay, now I'm going to put it all together. First, the x terms. So the net force in the x direction is 0, and that's equal to, now I'm going to add up all of these forces. 0 plus 0 plus 350 plus 385 minus F. And in the y direction, that's 0 is equal to plus n. Oh, wait, hold on. I made a mistake here. This should be a minus sign, minus the weight. Sometimes you get too busy, too caught up writing down these things, and the rest of the forces are 0. 0 plus 0 plus 0. So you solve these algebraically. The normal force strength has to be 2943, and the friction force strength has to be 350 plus 385, 735 newtons. Okay, so here's where things get fun. You know that this is kinetic friction. And so it's related to the normal force according to this law. Fun. No. Friction, that's a mu, that's an n. So technically this is pronounced 735 is equal to mu times 2943. So the coefficient of friction between the floor and the and the safe is 0.25. That's my answer. Move on to the next question. 27. All right, 27 goes like this. A 1,000-kilogram car traveling at a speed of 40 meters per second skids to a halt on a wet concrete where mu kinetic is 0.6. How long are the skid marks? Okay. So you got a car. It's got a velocity. And it's going to stop. The question is, how much time? How far does he skid to a stop? To answer that question, we need to know what the acceleration is. And so to figure out the acceleration, we need Newton's laws. So we're going to use the same technique as we did before. 1. What's the acceleration? I don't know what the acceleration is, but I know which direction it is. I know that the acceleration is probably in that direction, right? So I'm going to represent it as a capital A. I don't know what it is, and I'll put a minus sign there. Okay, step 2, net force. F net in the x direction is going to be 1,000 kilograms minus 1,000 times A. F net in the y direction is 0. 3. Let's map out all the forces. You got the force of friction, you got the normal force, and you got the weight. The weight in the x direction is 0. The weight in the y direction is minus 9810 newtons. Normal force, I don't know how big that is. I know that it's straight up though. Oops. So I'll call it plus little n. And then the friction force, I don't know what is, but I know what direction it is, minus F. In fact, I know that this is the kinetic friction, so it should be mu times n. Or in this case, they're given 0.6 minus 0.6 times little n. So when I find little n, I can figure out what this value is. Force in the y direction is 0. Now I put it all together. So the x components are that one minus 1,000 times a is equal to, now I add up these x terms. 0 plus 0 minus 0.6 times n. And then the y direction, it's 0 is equal to minus 9810 plus little n plus 0. And you solve these algebraically. Little n is equal to 9810 newtons, and the acceleration thus must be 9810 times 0.6, 5.89 meters per second squared. Okay, now we're going to put it to use. I know I have an object. Its initial velocity is plus 40 meters per second. Okay. And I know that its acceleration is in that direction, minus 5.89 meters per second squared. I want to figure out how far it is before it stops sliding. Okay. There's a couple different questions. This is a constant acceleration problem. And we're familiar with these. Let's find out what the time. So if this is t is equal to 0, let's see what time you stop rolling. V is equal to 40 minus 5.81 times t. So V is equal to 0 when t is equal to 6.88 seconds. Oh, snap. Hold on. Give me a second here. I'm going to turn off my mic. All right. Sorry about that. Yeah. Okay, so let's see, where were we with this? This is how much time it takes to slide to a stop. So delta x is equal to v initial times t plus a over 2t squared. So let's see how far it's gone. So this is 40 times 6.88 plus minus 5.81. It should be 5.89. 6.79. Oh, I'm at the end of the page here. Oh, geez. Well, you just plug in the numbers. I'll do that right now. So it's 40 times 6.79 minus 5.89 times 0.5 times 6.79 times 6. So 136 meters. That's how far you slide. Weird, eh? Okay, so question 30 now. Question 30 goes like this. What's the minimum downward force on the box in figure 3.0? Okay, so 3.0 looks like this. 30 F, and then a rope, and this one's pulling at 125 newtons. Okay. It says, what's the minimum downward force on the box in this figure that'll keep it from slipping? The coefficients of static and kinetic friction are given. Static friction, it's 0.35, and kinetic, it's 0.25. Okay. So, the deal here is that we want the object to stay stationary. And that means static friction. Alright, so kinetic friction, that's a red herring. Doesn't matter. Okay, so let's start the analysis. If it's stationary, what's the acceleration? In the x direction is 0, and the y direction is 0. 2, what's the net force? F net in the x direction is 0, F net in the y direction is also 0. Step 3, label all the forces. There's gravity, there's the normal force, there's the force pushing down, okay. There is also tension pulling to the right, and then friction presumably pulling to the left, okay. So now let me write out all these forces. Normal force in the x direction 0, normal force in the y direction, I don't know what. Tension in the x direction is given 125 newtons. Tension in the y direction is 0. Weight in the x direction is 0. Weight in the y direction is 9.81 times 30. So it's minus 294 newtons. So that's the weight. The force, I don't know how big that is. So it's the force in the x direction is 0. The force in the y direction is, I don't know how big this is. I will write it as capital capital F, push. Well, I don't just call it P for push, because I'm pushing it down. Sure. Okay, so P is for push, that's how big the force is, and it's in the minus direction. Finally, the static friction force in the x direction, that's not given, and the static friction force in the y direction is 0. So now I'm going to put all these pieces together in the x direction. So net force is 0. So that's 0 plus 125 plus 0 plus 0 plus, oh, this is a minus number, minus that force. And in the y direction, it's 0 is equal to n plus 0 minus 294 minus p plus 0. Okay, so let's continue putting these together. Evidently, the force here from friction has to be 125. Okay. And there's two variables in this case. So that's, I don't know, normal force is equal to 294 plus p. That makes sense. Okay. Now to finish the question. The question is asking, what is the minimum amount of force where this friction can hold it in place? Well, the minimum amount of force is, hold on, which question is this? 30. The minimum amount of force, P, so P determines the normal force, but we'd be talking about it if this were the maximum friction, static friction. The maximum static friction is the normal force strength times, in this case, 0.35. That's mu static. Okay. So you see how the normal force enters into the calculation for the maximum amount of force. So it's 294 plus the force I'm pushing down times 0.35. So if it's the maximum amount, it means that I'm pushing P on hard enough so that the maximum force, you know, the bigger the pressure I put on it is, the bigger the maximum force is going to be. So maximum force is 125, and now I just have to solve for P. .63 newtons. There's my answer. Next question. Question 32. Let's see if anybody's watching or in the live chat. Oh, one person's watching. Hello, one person. Okay, so question 32 goes like this. A 22 centimeter diameter bowling ball has a terminal speed of 77 meters per second. So this is 22 centimeters. Oh, it's 11 centimeters in diameter. So this is 0.11 meters in radius. Okay, so it says that this is and the question is, what's the ball's mass? So let's analyze this the way we analyze a lot of things. This is actually a one-dimensional problem, so you can just put the x-axis like this if you want. It's fine. So the acceleration in the x direction is 0. It's moving at a constant velocity. So F net in the x direction is 0, which means all the forces are balanced. What are the forces on the object? There's drag and there's gravity. So the drag force is equal to, let's do a thing. It's written down here. The drag force is 1/4 mu, or rho, AV squared. So we know the velocity of this. In fact, you know all these terms. Rho is, actually this is in the x direction. 1/4. Rho is the density of air, which is given here somewhere. All right, 1.22 kilogram per meter cubed. The area is going to be pi r squared, 0.11 times meters squared. and the velocity is 77 meters per second all squared. So let's put all these into a calculator, see what we get. 1.22 times pi divided by 4 times 0.11 times 0.11 times 77 times 77. 68.7 newtons. All right, and the weight is minus 9.81 times the mass. Now, time to put it all together. You'll note that I don't know the mass, so that's a variable. Time to put it all together. F net is equal to 0. Add up the forces. Plus 68.7 minus 9.81 times m. And you solve for m. Seven kilograms. All right, now it's time for question 35. Blocks with mass 1 kilogram, 2 kilograms, 3 kilograms are lined up in a row on a frictionless table. 1, 2, 3. All three are pushed forward by a 12 Newton force applied to this block. How much force does the 2 kilogram block exert on the 3 kilogram block? So I want that force on this boundary, on the 3 kilogram block, and how much force does the 2 kilogram block push on the 1 kilogram block? Those are the questions. Okay, so how do I analyze this? So before we go on, I think that this is a one-dimensional motion question, x. I mean, so it's frictionless, and that means the normal force, okay, it's frictionless and horizontal, which means it's not going to accelerate in the y direction, because the normal force is just going to balance gravity. And also the normal force doesn't really enter into the calculation anywhere else. So I'm just going to do it in the x direction and ignore the y direction. It doesn't really affect the motion. Step 1. What's the acceleration in the x direction? I don't know. Okay. And at this point in the game, I go, oh hey, there's 3 blocks here. Block A, block B, and block C. That means I have to draw three body diagrams and a whole bunch of things. So, because they're 3 interacting objects. So I'm going to call this A1, X, A2, X direction, A3. Wait, ABC. That's why I did that. I'll call this A, B, C. Okay, so all the blocks are moving together, and that means they're going to have the same acceleration. So already, there's stuff I do and I don't know. I do know that they're moving together in a group, which means they're going to have the same velocity, which means they're going to have the same acceleration. I don't know what that acceleration is. The net force in the net force x FC net. They're all going to feel different amounts of force. How is that possible? Well, they are. So the net force can be found by multiplying the acceleration by the mass. So the first one is A, the second one is 2A, the third one is 3A. Step 3, free body diagrams. So A, B, C. Each of these is going to get their own free body diagram. So this one, A, it feels a push 12 newtons. And it's also going to feel a force from B. I'll call it FB. Okay. How about FB? FAB. The force between A and B. Yeah, I like that. So F push in the x direction is equal to plus 12. And FAB is in the minus x direction. So I'll call it minus F. Next free body diagram. Well, nothing specifically. No other person is pushing it. So those are just the two surfaces on either side. So there's FAB, which points this way now, and FBC, which pushes this way. What do I know about them? Well, I know which direction they're pointing. FAB points to the right, and it has the same magnitude as this, so I'm going to use the same variable. I don't know what variable to use this. I'll call it P for push. All right, C's free body diagram. There's only one thing pushing on C, and it's pushing this way. It's the force BC. Wait, hold on. That's supposed to be a minus sign. So this is push. And now we're going to put all the information together. This composes the net force on A. This composes the net force on B. That's the net force on C. So A is equal to 12 minus F. 2A is equal to minus P plus F. And 3A is equal to P. And now we just need to solve these algebraically. I'm going to combine these two together. So this is 2A is equal to minus 3A plus F, which in turn becomes 5A is equal to F. And now I'm going to take this guy. Hold on. A is equal to 12 minus 5A. Rearrange that. 6A is equal to 12. So A is equal to 2. And now that I know that, I can find the force F, which is the force from A on B. And so that's going to be equal to 10 newtons. And once I know that, I can figure out, that's not what I wanted. Oh, here. So that's 6 newtons. Does that make sense? Let me draw each one in turn so you can get a sense of why and what's going on. Okay, so box A, box B, and box C. 1 kilogram, 2 kilograms, 3 kilograms. There's one force pushing this one to the right with 6 newtons. So the acceleration of block C is going to be 6 over 3, 2 meters per second squared. On box B, there's two forces. One of them pushing to the left with 6 newtons, and the other pushing to the right with 10 newtons. And so the net force is going to be plus 4 newtons to the right, and the acceleration is F divided by m is going to be 4 over 2 plus 2 meters per second squared. They all have different amounts. Okay, so then A is going to have two forces on it. One pointing that way, that's 10 newtons strong, and then one pointing this way, that's 12 newtons strong. So F net is plus 2 newtons, and the acceleration is 2 over 2. Wait, 2 over 1, that's 2. So you see they all have the same acceleration. Does that make sense? Okay, I hope so. That's question 35. Time for question 36. Question 36 goes like this. What tension in the rope in figure... And then they drew the figure. So here's what the figure is. It's a rope and a pulley and then 100 kilograms. And this one's 60 kilograms. And this is sitting on the floor. Okay. So, one question you can ask is, hey, the force of gravity counters, the force of tension counters gravity. Whose gravity does it counter? Does it counter both of theirs or what? Because they feel different amounts of weight. So in both of these objects, me, box, me, box. How many forces are acting on me? There's weight, and then there's tension pulling up. How many forces are acting on the box? Well, there's weight, there is tension, but there's also a possible normal force, okay, because it's also touching the ground. And so what this means is that the tension force here doesn't need to be as big as the weight is, because the normal force can also help cover the downward going force. Okay. So in both these cases, the acceleration is 0. But we're going to use this one to calculate the tension, because in this one, I know the acceleration is 0, but I don't know what the normal force is. And so there's two things I don't know. So in this one, the acceleration 0, net force, oh, come on, F net is also 0. Got the x-axis. So the weight, how about x-axis going? It's up instead of down. That's a little confusing. So the weight in the positive x direction is minus 9.81 times 60. .588.6 newtons. Then the tension force in the x direction is unknown. So because the net force is 0, tension minus 588.6. So the tension has to be 588.6 newtons. So this tension is pulling this one up with 588 newtons. Tension's pulling this one up at 588 newtons. Of course, the 588 newtons isn't enough to hold up the weight of the 100 kilogram box, but the normal force helps with that too. 38. Figure blah shows two 1 kilogram blocks connected by a rope. A second rope hangs beneath the lower block. Both ropes have mass. Ooh. Okay, you know what? I'm gonna scratch 38 from the thing, just because it's not a massless rope, and when you enter mass into the ropes, it's straightforward, a calculation, but it's also I don't think we're gonna test you on it, so it's not testable. I don't like those questions. So the next question is 46. Oh. 46 reads, a 50-kilogram box hangs from a rope. What's the tension in the rope if the box moves up at a 75 meters per second, or if the box has Vy's 5 meters per second is slowing down at a given acceleration? Okay, so part A. I guess we're using this as the y-axis. Okay. So A in the y-axis, what is it? The acceleration in the y-axis. In this case, it specifies the rope is moving at a steady 5 meters per second. That means it's not changing. That's what those words mean, not accelerating. So 2, F net in the y direction must also be 0. Let's talk about the forces on the object. 3. There's the weight and the tension force. Only those two. Tension force in the y direction is plus tau. I don't know how big it is. And weight in the y direction is minus 490.5 newtons. Now we put it all together. Net force is equal to the tension plus gravity. So the tension has to be 490.5 newtons. Part B. Reproduce the question, only this time the box has velocity 5 meters per second and it's slowing down at 5 meters per second squared. So the acceleration is minus 5.0. 2. Net force. Going to multiply the acceleration by the mass. Minus 250 newtons. 3. Write out the forces. Weight, tension in the y direction. I don't know what so I'll call it tau. Weight in the y direction is 490.5. Now I put it all together. So the tension has to be 240.5 newtons. Okay. Question 54. A 2-kilogram, oh, this question's great. A 2-kilogram child goes down a straight slide, inclined 38 degrees above the horizontal. A child is acted on by his weight, the normal force, the slide, kinetic friction, and a horizontal rope exerting 30 Newton force as shown in the figure. How large is the normal force on this slide? If mu kinetic is 0.5, what is the acceleration? This question's marvelous. Here, I'll draw a drawing of it. You got a slide, it looks like this, 38 degrees, and then you got your kid, it looks like a mass, and then there's a rope staying horizontal pulling with 30 newtons. I'll tell you why this is an interesting question. This question's interesting because the friction depends upon how strong the normal force is. And the normal force depends on a bunch of different forces, like, for instance, gravity, but also this guy. That's going to decrease the amount of normal force the system feels, and so it's going to change the friction. So I want to add this part of the question because I think this question's a good one, and we could go a little bit further. If I also know the coefficient of kinetic friction, sliding friction, what is the acceleration? Okay, so how do we do these problems? You know what? I think this is probably better for it. Okay. First I'm going to draw the x and y axes. I'm going to do it this way. It's helpful. There's an advanced trick, and the advanced trick is if you point your x direction in the direction of the acceleration, sometimes it makes questions easier to do. So that's my justification for it. In context of these, what's the acceleration? Acceleration in the y direction, acceleration in the x direction. Acceleration in the y direction is 0. I don't know what the acceleration in the x direction is, but I know it's downslope. 2. Net force. So the net force in the y direction is 0, and the net force in the x direction is, what's this kid's mass? 23. 3. Let's start listing all the forces. Sometimes it's helpful when you're drawing one of these diagrams, especially if you have more than one color, to draw the x and the y axis. And then draw your forces over top in a different color. Only forces are supposed to be drawn on the free body diagram, but the point of the free body diagram is it helps us figure out what the components of the force are. So the friction force points in that direction. The normal force points in that direction. Weight points in that direction. And the pulling force goes that way. So even though the pulling force is horizontal, we have to represent it as a mixed vector. Before I go too much further, it might help if I suss out what the angles are here. So this angle here is 38 degrees. And this angle here is 38 degrees. This is from, Greek-style geometry. Do you want me to explain it? I've explained it in class, but nobody ever remembers when I explain these things. Okay, so here's our slope. This angle here is 38 degrees. Imagine I make a triangle. I'm trying to make a triangle, a right-angled triangle, where our vector is the hypotenuse. Okay? So you'll note that because this line is vertical and this line is horizontal, it makes a right-angled triangle. So this angle here has to be that angle there plus 38 have to add up to 90 degrees. Because this angle here is a 90-degree angle. So this angle and this angle have to add up to 90. But here's another right-angle triangle. This right-angle triangle, this angle and this angle have to add up to 90. And that means that this angle and this angle are the same. They're both 38. What about the other one? It's important. I mean, if you can think on your feet through these questions, it's pretty helpful. Here's the slide, 38 degrees to the horizontal. Here's the rope. We know that the rope is parallel to the horizontal. And so because this line, straight line, bisects both of them, this angle here has to be 38 degrees as well. Isn't that fun? Yeah, you should phone your high school math teacher and thank them for teaching you Greek geometry. Okay, let's write out all these forces. Force of kinetic friction, I don't know, but it's pointing in the minus x direction. So it's got 0 in the x, and then in the y direction, oh yeah, hold on, normal force. Normal force in the x direction is 0. Normal force in the y direction, I'll call it little n. If I knew what this was, I could figure out what this was. Mu kinetic times little n. There's also weight. This is going to be mg sine of 38. This is mg cosine of 38. And it's in the negative direction. Similarly, F pull in the x direction, you decompose that, and it's 30 times cosine of 38. And F pull in the y direction is 30 times sine 38. And now we put it all together. So the x components is 23 times acceleration, and that's going to be mu k. I guess mu k, I've already been given that, so it's 0.5 times n plus 0 plus, okay, so I'm going to calculate these values. I don't want to waste too much time doing it, so I'll just do it now. The mass here is 23 kilograms times 9.81 times sine of 38. That's 139 newtons plus this one. So it's 30 times cosine of 38. 23.6. Y components. 0 is equal to 0, it's that one, plus little n minus, alright, so now I'm going to calculate this one. 23 times 9.81 times cosine of 38, that's minus 178, and then I'm going to calculate this one, so that's plus 30 times sine of 38, 18.5. Alright, so now I do the calculation and put it all together. N is equal to 178 minus 18.5, 160 newtons, and then the acceleration, plug this in here, acceleration is going to be 160 times 0.5. Oops, hold on. This needs a minus sign in front of it. Minus sign. Alright. 160, no. Plus 139 plus 23.6. So the acceleration is going to be 82.6 divided by 23. 3.6 meters per second squared. Alright, so the question asked how big the normal force was, and this tells us that the normal force must be this. And then based on the other things, you can tell that the acceleration has to be this. Pretty fun, right? I had fun. Nobody has any questions? Alright. Only 4 more to go. Question 60. Whoa. A person with compromised pinch strength in his fingers. Here, I'll draw the picture. So this is a hand getting all pinchy. And there's a book in between. Okay, so it says, a person with compromised pinch strength in his fingers can only exert a normal force of 6 newtons to either side of a pinched object. I guess that means that this force is 6 newtons and that force is 6 newtons. Such as the book. What's the heaviest book he can hold on to before it slips out of his fingers? The coefficient of static friction is 0.8. So the deal here is that I'll call this the thumb, and I'll call this the index finger. Okay? Both of these are applying a force to the object. What's the object here? The object's the book. Both of them are applying a force to the object. Both of them will also apply a friction force to the object. So which object are we talking? Okay, so what's the book's acceleration in the x direction? What's the book's acceleration in the y direction? They're both 0 because the book is staying still if we are lucky. What's the net force in the x direction? What's the net force in the y direction? They're both 0. Multiply m by that, it's 0. Okay. Let's draw all the forces. There's the force from the index finger. There's the force from the thumb. There's the weight. There's the gravity. There's the friction from the thumb. And then there's friction from the index finger. Okay? So, we're talking about the max weight, right? So in other words, the friction on my thumb should be equal to the maximum friction possible. And we can have it, there's an equation for calculating the maximum friction possible. Hold on, please. Okay, so this is an aside. So let's start calculating. Weight in the x direction is 0. Weight in the y direction is minus g times m. Force from the thumb in the x direction is minus 6 newtons. Force from the thumb in the y direction is 0. Pressing force, there's going to be friction. We'll count it separately. Force from the index finger in the x direction is plus 6 newtons. Force from the index finger in the y direction is 0. Force from the thumb, friction in y direction, I'll call that plus F max. Force from the index finger in the y direction is plus F max. Okay, on the side here, you don't gotta write down all the components. If most of them are 0, you don't have to write them. I'm kind of running out of space, so I'm just going to go with that. The other ones are implied 0. Let's put it all together. So the x components, it's 0 is equal to 0 minus 6 plus 6 plus 0 plus 0. It's equal to 0. Fine, I don't need to work on that. What about the y direction? Acceleration is also 0, force is 0. So this is going to be minus 9.81 times the mass. Okay, right. So plus F max I t plus F max t plus 0 plus 0. Okay, so here's the fun part. The maximum amount of friction force is going to be the pressing force, which is 6, times 0.8, the static friction coefficient. It's 4.8 newtons. And it's going to be the same for both. I, F max, T, because the pressing force is the same. So this equation becomes 9.81 times m is equal to 4.8 plus 4.8. So m has to equal 0.98 kilograms. Questions? Nobody has questions. Okay. So, let's do 61. A 1 kilogram block is pressed against a vertical wood wall by a 12 Newton force as shown. If the block is initially at rest, will it move upwards, downwards, or stay at rest? So... okay. All right, so that's what we're given. So, what object are we trying to describe? We're trying to describe the block. That's 12 newtons. Okay, so what's the acceleration in the x direction? What's the acceleration in the y direction? We're pretty sure the acceleration in the y direction or the x direction is 0. Not going to press into the wall. As for the y direction, I don't know. Let's just call it plus a. Okay. Might be positive, it might go up, might go down, I'm not sure. F net in the x direction is 0. F net in the y direction is 1 times a, so that's a. Let's start talking about the forces. There's weight. There's the normal force from the wall. And then there's this pushing force, which is 30 degrees. Weight in the x direction is 0. Weight in the y direction is minus 9.81 newtons. Normal force in the x direction is, I don't know, plus n. Normal force in the y direction is 0. F push in the x direction is, let's see, it's 12 newtons times cosine of 30. So that's minus 10.4 newtons. And force push in the y direction is six newtons. All right. So now we put it all together. The x components, net force is 0. In the x direction, it's 0 plus little n minus 10.4. In the y direction, it's a is equal to minus 9.81 plus 0 plus 6. All right, so already, I mean, hooray, we know what the normal force is. So at this point in time, you're probably asking, what about friction? And indeed, if there was a friction force here, the friction force would probably be pointing in the positive y direction, although who knows? We don't know anything about the friction force. They haven't told us that there's a friction force, so I suppose we're supposed to assume that there's no friction force, which is why there's only 3 forces. In this case, minus 3.81. The acceleration is going to be negative. It's going to go down. So, next question is question 65. Two blocks are at rest on a frictionless incline. Well, at least they told us. 20 degrees. What are the tensions of the two strings? Oh, this is a fun one. Okay. $20. This one's 5 kilograms. Call this 1. And this one's 3 kilograms. And then it's attached with 2. Alright, you ready for some fun? Sure you are. I'm going to make the x-axis point in this direction and the y-axis point in this direction. There's 2 objects, so we have to analyze them independently of one another. I'll call this box A and box B. X0, A, Y, 0, A, B, X, 0, A, B, Y is 0. They're not moving, and they're staying not moving, so the acceleration is 0. F net, A, X is 0. F, oh, come on. Alright, so the net forces are all 0. Now for the fun part. Let's draw their free body diagrams. Block A, block B. It feels a weight. What else does A feel? Normal force? What else does A feel? Tension, pulling it up. Tension. And got to draw my x and y axis. X is that way, y is up. Okay. I'll call this T1. And then what forces does B feel? It feels a weight. Okay. It feels normal force. It feels a tension force pulling it up the slope, T2, and it feels a tension force pulling it down the slope, T1. So now we just have to write some forces out, okay? Let's see. So the weight for the first one in the x direction, weight for this first one in the y direction are 9.81 times 5 times cosine of 20. That's minus 46 newtons. 9.81 times 5 times sine of 20. Normal force in the x direction is 0. Normal force in the y direction, I don't know how big that is, little n. And T1 in the x direction is minus, I'll call it tau. T1 in the y direction is 0. So let's put it all together with these ones. So the x components are 0 is equal to 16.8 plus 0 minus tau. In the y direction, it's 0 minus 46 plus little n. Little n. Time to do this one. W in the x direction, W in the y direction, N in the x direction, N in the y direction, T1 in the x direction, T1 in the y direction, T2 in the x direction, T2 in the y direction. Okay, so 3 times 9.81 times cosine of 20. That's this number here, minus 27.7. 3 times 9.81 times sine 20. That's equal to 10 newtons. Normal force in the x direction is 0. Normal force in the y direction, I'll call it NB. Tension force in the x direction. Here's where things get fun. I don't know how big this tension force is, but I do know that it's the same strength as here, which means I need to reuse that variable. So it's plus tau. 0. Similarly, I don't know anything about this one. So in the y direction it's 0. In the x direction it's how about if I call it P for pull. Okay, now I'm going to put all these together with these. Okay, so in the x direction it's 0 is equal to 10 plus 0 plus tau plus p. Wait, hold on. This has a mistake in it. It's supposed to be minus p because it's pointing downhill, or it's pointing in the negative x direction, which is uphill rather. Okay, and the other one, 0 minus 27.7 plus nb plus 0 plus 0. Alright, so now we just solve these equations together. These two, these tell me the normal forces. This one tells me that tau has 16.8. That tells me the tension in the second rope. And then the tension in the first rope, in the top rope, has to be 26.8 newtons. See? Okay. Any questions? Which one was that? That was 65. Alright, one more to go. This marathon of questions. 70. 70 reads like this. 2 blocks are connected by strings in figure 5.7. What's the upper box acceleration if the coefficient of kinetic friction between the block and the table is 0.2? This is 1 kilogram. Call it B. A, it's 2 kilograms. And the velocity is like that. Okay, so what do I know here? I got 2 objects. A in the x direction, A in the y direction, A, B in the x direction, A, B in the y direction. So what do I know? The first thing I know is that block A isn't going up and down, it's going side to side, so its acceleration in the y direction is 0. Block B isn't going side to side, it's only going up and down, so its acceleration is 0. What else do I know here? I don't know what the acceleration here is. I'm going to have to assume a value for it, but I know it's side to side. So let's suppose it's accelerating that way, just for fun. So that's x, y. So let's assume that this one's accelerating in the x direction, in the positive x direction. I'll call it accelerate. If that's the case, then this one, because they're attached together with a rope, their speeds have to be the same. So the rope stays the same length. So if this one moves to the right without acceleration, this one has to have the same amount of acceleration. So this one, let's call it plus little a, and this one we'll call it minus little a. From this we can find the net force. Okay, so the net force in the y direction on A is 0. The net force on the y in the x direction is 0. The net force on A in the x direction has to be the mass times A, so it's 2 times A. And the net force on this has to be the mass times that, so it's minus 1 times A. Let's analyze all of the forces on them. So for A, what are the forces? You got friction, sliding friction is going to go that way. So kinetic is normal force. There's gravity. And there's tension. Except that we don't call it gravity, we call it weight. For B, there's only two forces. There's tension pulling it up and weight pulling it down. So let's write out the different forces. Force, kinetic, wait, start with the weight. Weight in the x direction, weight in the y direction. So weight in the y direction is minus 9.81 newtons, and the weight in the x direction is 0. Tension in the x direction. I don't know what that is, but I know which direction it's pointing. It's pointing none in the y direction, probably to the right. I'll give it the variable tau, just because I need to label the things I don't know. Normal force in the x direction is 0. Normal force in the y direction, I'll label it with little n. I don't know its value either, but I know it's in the positive y direction. Friction. Ooh, weird. Super weird. Friction in the x direction, minus, if I knew what this number was, I would be good to go. So it's minus 0.2 times little n. Friction in the y direction is 0. Tension in the x direction is 0. Tension in the y direction is, I don't know what it is, but I've already labeled its value, tau. So plus tau. Weight in the x direction is, oh wait, hold on, I did this wrong. Alright, hold on, I'm gonna just, okay, mistake. Alright, the second block, its weight in the x direction is 0. Its weight in the minus 9.81 newtons. Alright, the weight of this guy, it's got a mass of 2 kilograms, 2 times 9.81. So its weight is minus 19.6. Alright, let's put these together with this info. Start with A in the x direction. 2A. 0 plus tau plus 0 minus 0.2 times little n. Y direction. Acceleration y direction is 0, so the net force is 0. And so this is minus 19.6 plus 0 plus little n plus 0. Now for B, in the x direction, acceleration 0 plus 0 plus 0. In the y direction, it's minus little a is equal to plus tau minus 9.81. All right, so let's solve this. We want to know what the acceleration is, right? So we can use this equation to figure out what the normal force is. 19.6 newtons. Once we know that, we can plug this into up here. And we end up with two equations. 2a is equal to tau minus 0.6%, 3.92 newtons. I'll leave the units off here because there's a lot of stuff going on. And the second one is minus a is equal to tau minus 9.81. So I'm going to solve these equations. The fastest way to solve them is to multiply this one by minus 1 and add the two expressions together. And you get 3a is equal to 0, 9.81 minus 3.92 plus 5.89, and the acceleration is that divided by 3, 1.96 meters per second squared. And that concludes question number 70. So I hope you had fun. I hope you watched this. Hope you learned something from it. Lots of examples to work through. You'll see that the method that we've been using to solve these problems is pretty straightforward. It's the same method for all of them. The tricky parts are recognizing the clues about the acceleration. The tricky parts are being diligent about writing everything out. And the tricky parts are, well, you know, figuring out what type of friction it is and stuff, recognizing which forces are on it. All right. Thank you very much. Have a good evening.